Okay, so far we have been discussing Green's theorem. Again, remember the point of Green's theorem is that say you have this curve on the xy plane and you want to compute the work of a force field along this curve. And what Green's theorem says is that instead of choosing to do the actual integral, you can do a double integral over the region determined by this curve. Okay? And so this is assuming that we're working on the xy plane, right? But now we can do something else, which is, let's imagine that actually this curve is like in space. So it's not just like drawn on the xy plane, but you are allowed now to move in the z-axis, along the z-axis, which is here, or more precisely, the z-axis is pointing towards you, right? So if that's the case, there's actually, how can you think of this region? So this region is a region, let's color it. So imagine that the YouTube conspiracy theories are true, and we actually live on a flat Earth. Then you're a flat earther and you're driving on your flat Earth, and the point of this curve is sort of, you should think of it as the end of the world, right? That's where you would hit this wall from after which you cannot go through. So you can think of a curve when it bounds some region. The curve is like, this boundary is like the frontier of your region, right? Okay, so why do I say that? Because now if you're in space, not just on the xy plane, there are more interesting surfaces whose boundary is the same curve. So what do I mean by that? So it was cheaper on Amazon with the smiley face, but imagine that you have, so again, you have this pink curve, but now think of this green surface coming from this net. Okay, so again, now we are not flat earthers. We live in a weird, on the surface of a weird region, which is this green stuff. Okay, and if you live on this surface, as again, you can drive on this surface, and you can drive happily along this surface, but eventually you hit the boundary, right? If you keep driving. And so the boundary of this planet, right, of this net, is really the same boundary as this green region. And the miraculous thing, and this is a really cool thing about Green's theorem, or it's actually its 3D version, which we're about to discuss, which is Stokes' theorem. The really cool thing about Green's theorem is that or Stokes, is that it says that if you wanted to compute the work for this pink curve, you could use a double integral over this region, which is what we have been doing, or you can actually integrate something along this surface. So you can do what we will call a surface integral. Okay, so let me just write it this way. So what Stokes says, what Stokes' theorem says, is that if this is a closed curve, right, the work along a closed curve that work equals integral, a surface integral, S of something ds. Okay, where S is a surface, any surface whose boundary is the curve C. Okay. And again, you don't have to imagine the curve is an actual circle. I just use a curve because that way I could match it with that thing, the net. But in general, it does not need to be a circle, right? It could. What I'm saying is that if you have any curve, any closed curve in space, and you want to find the integral along the work done along this curve, then you can really just like cap it off and find a surface, a planet whose boundary, whose frontier is this curve. Okay? And so actually Stokes' theorem is like one of the major theorems of the class. Like the other major theorem is the divergence theorem. So really this is more will be on the final exam. What we want to do for now is just find the statement of Stokes' theorem, and then we have to break it down into pieces because it has a lot of information. So we will focus first on some of the individual pieces of Stokes' theorem, but until the very end we will return to it and apply it in its full generality. So how you should think about Stokes' theorem? Well, again, if you remember what we did for Green's theorem, what would the statement of Stokes' theorem be? Like we have to find what you should put here, and I still have to explain what I mean by a surface integral. You should just think it's like a generalization of a double integral, but now not done on the xy plane. But in the case of Green's theorem, what I did, if you remember, was to break the region into small rectangles. Okay. And then I just had to understand the theorem in the case of tiny rectangles. So here you have something analogous. You want to understand Stokes' theorem for this surface, okay? And instead of understanding it for this surface directly, what you do is cut the surface into tiny, tiny, tiny rectangles. So you have some surface here, which is like the one that you see on this picture. And you cut it into tiny rectangles. It's just that these rectangles are no longer like actually flat, right? They're wobbly rectangles. So for example, the kinds of rectangles I have in mind, imagine like the surface is like half one of the hemispheres of Earth. So like say the northern hemisphere. Okay? So the rectangles that I have in mind for here are rectangles which would look something like this. Okay? And so, they're like bended. They're not flat. There's some bending to these rectangles. But the cool thing is that really, here's one way to think about these rectangles. So here we have X, Y, C. So imagine that you have like a flashlight, and from this flashlight, you look at the projection of this tilted this bended rectangle on each of the planes. So what I mean by that is that this yellow stuff will create some shadow, which does look like, well, more or less like some curvy rectangle maybe, but it's like flat because it's being projected to the XY plane. So it's like an actual flat thing. And so here's like a projection, here's like the shadow. Okay? But the shadow on XY plane but there's another shadow here on the XZ plane. And there's another shadow here which is harder to draw because but there's another shadow here on the YZ plane. Again, this is like a heuristic argument, so doesn't matter not every single detail makes sense of what I'm saying currently. But the point is that on each of these individual planes, you have like flat things. There's no bending, so you can apply Green's theorem to each of them. And if you remember, if you think of the vector field, now we're in space, so the vector fields that we're studying, they're more like the original ones we started when we talked about work. They had three components, right? So here's like F, maybe here's F, here's F, here's F. So we had three components, and if you remember, for Green's theorem on the plane, you only have, when you're on the plane, only the first two components matter. And the point is that in this case, Green's theorem involved a double integral related to the partial derivative of f2 with respect to x minus the partial derivative of f1 with respect to y. Okay? And what you would find actually, there's like a Green's theorem version for each plane, and on this plane the components that matter are x and z, right? So f2 and f3. So basically what you would find is that the Green's theorem in this case involves the partial derivative. I may get one of the signs incorrectly, but it will involve the partial derivative, say, of f3 with respect to x minus the partial derivative of f1 with respect to z. And finally, here is a yz plane. So you're looking at these two components, and what Green's theorem would say is that you have to look on this plane. What would appear is a term that involves like the partial derivative of f3 with respect to y minus a partial derivative of of f2 with respect to z. So what I'm trying to say is that there's a Green's version for each plane, for each term of these mini planes or mini rectangles that you get, and then if you wanted to know what's going on the surface, you have to sort of combine all these different contributions coming from the individual Green's theorems, but not all contributions should matter the same amount, because maybe, for example, it could be like maybe the surface happens to be parallel to the xy plane. If the surface happens to be parallel to the xy plane, right? Let me draw it here. Imagine that your surface is actually parallel to the xy plane, like this. Maybe you just moved your surface a little bit. Well, clearly the only shadow that matters in this case, when you draw one of the tiny rectangles, the only tiny rectangle that matters is this one, because the other shadows actually become lines. Okay? So somehow you need to take into account this phenomena, and what takes into account that is a normal vector. So remember that to every surface there's a normal vector, this one. Okay, and basically the normal vector will indicate how much each plane should matter in the statement. So again, I'll just write the statement of Stokes' theorem. It's not something you have to worry too much at the moment. I just want you to have like an idea of where we're headed. And once I write the statement of Stokes' theorem, I'll tell you what we need to know from it in the immediate future. So here's the statement of Stokes' theorem, the actual statement. So you have, let's see what Stokes says. Again, you don't have to worry about precisely the content of the theorem for now, because we will revisit it later. But what it's saying is, imagine that you have a surface like the northern hemisphere of Earth, or this surface, or again this green surface, right? And the surfaces have a boundary, which is a curve. In this case, happens to be a circle, but that's not indispensable. It could be like a more weird curve. The only thing that matters is that it is a closed curve. And so what Stokes says is that the work, and since I don't need the precise statement right now, I won't write all the details, but what this is saying is that the work, sometimes when you are working with closed curves, you draw like a circle on the integral to indicate that. So the work, which is this, so this is work closed curve. Well, it happens to equal a surface integral of, before, remember, this was an integral over the region enclosed on the xy plane by the curve. Now what I'm saying is that you can replace that region on the xy plane by any surface that bounds, whose frontier is this particular curve. So this is going to be a surface over S of what? Here's the magic thing that you have to put. Is something that's called the curl of the vector field. Okay, and so here, n is just, okay, what is n? N is a vector normal to the surface, a unit vector, and again I'll repeat this later because for now this is actually not the most important part, but it's a unit vector normal to the surface. Okay, and we actually know how to find these because we found tangent planes to surfaces. And in order to find tangent planes, we had to find the normal vector. Remember, that involved the gradient of the equation of the surface. I'll tell you in a couple of videos how to find it differently, in a different way. But at least we know already one way to find the normal vector, and this is called the curl of f, which is now which is going to be a new vector field. Okay, and actually, what's the formula for the curl? Well, let me write it here. It has to be somewhere. Okay, yeah, but didn't I write it somewhere? Okay, let's see. Oh, okay. Well, I'll write it. I'll write it the way in which you end up memorizing it. So that's fine. Basically, the curl is going to be a vector field whose entries are these three combinations of things that appear on the Green's versions of the shadow version of Green's theorem. But that's going to be the end result. Let me just mention it here. In practice, the way basically I just have to place these formulas, these combinations in the corresponding slots. that's not like, but the thing is that you don't want to memorize these combinations. What you do, you think about this again as a cross product. This is why you're using the notation of cross product. And remember that we had this trick for finding the cross product, which was via this determinant of a 3x3 matrix where you put here I, J, and K. Okay? And so this is like A cross V. So B is the second vector, F, which is in this case F, and that just has entries F1, F2, F3, right? And what's more interesting is what you put here. Notice that this symbol is like the same symbol that appears when we computed the gradient of a function. Remember that the gradient of a function was just like the partial of f with respect to xi plus the partial of f with respect to yj plus the partial of f with respect to ck. Or in other words, the gradient of f was just partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. And then what you do now, again, is like a horrible thing, but it's useful, is like you sort of factorize f, which you cannot do, but it's like a linguistic game. You factorize it, again in quotes, and since f is on the same on both sides, you erase it, which again is a horrible thing to do, but it works, and like as a memorization tool, if you want to memorize the formula. So what you put instead of this symbol is just like the partial derivatives. So this is like a horrible formula on many levels. Strictly speaking, the determinant can only be determinant of numbers. Here on the first row we're putting vectors. On the second row it's not even clear what we're putting. And on the third row we're putting actual like numbers or scalar functions. So only one of the three rows is legit for the determinant. But the point is that the formula works just as well. And so if you apply the determinant formula here, you get the partial of f3 with respect to y minus the partial of f2 with respect to c. This is the one that appears here. Notice that this is, why would this component be here? This is the one that's related to the yz plane. The normal vector to the yz plane is a vector I. So I is the first entry. So here, the place where you place it is related to where the normal, with the corresponding normal vector. So now in the middle, remember that in the middle you have to be careful because it's plus minus plus. So in the middle really you have the partial of f1 with respect to c minus the partial of f3 with respect to x. Which is the thing that I had here, except for this convention with, this thing about the minus sign that you have to worry about in general. But this is basically okay. And finally, you get the partial of f2 with respect to x minus the partial of f1 with respect to y. And this is really this term which appeared in our ordinary Green's theorem. And again, the logic is that for the xy plane, the normal vector is z. And so you are recording here the fact that the normal vector to the xy plane is 0, 0, 1. Okay? So in the next video, I'll do an example with curl so that you see how it's computed in practice. But what does this funny thing buy you? And here's the main result, which we'll use next time. And finally, this answers our question on when a vector field is conservative. So here's the main result, which I won't explain. I will just say in words how this is supposed to go, but the point is that f will be conservative F is a conservative vector field if and only if this will become synonymous for us. There are a few exceptions, but the exceptions won't appear in this course, and I mentioned a little bit on the PDF, but sometimes you have to be a little bit more careful. But for our purposes, this will be true. So F will be a conservative vector field that will be equivalent to saying that the curl of F is a zero vector. And this is our desired way to detect if a vector field is conservative. So the point is that why would this be, like, at least let me explain why this could be true. Well, if the curl vanishes, if it always vanishes, then when you plug it into this formula, this right hand side will vanish regardless of how it's computed. And so this is telling you that the work on any closed curve has to be zero. And that's precisely the other characterization we had for being a conservative vector field. And the point is that if you're a conservative vector field, then you know that the left hand side is always zero, but then the only way for the left hand side to be always zero, regardless of the surface that you choose, is for the curl to vanish itself. So that's a very short explanation for something that would take a bit longer to go over in full detail. But the takeaway from this video is just like, oh, Green's theorem can actually be generalized to surfaces and curves. We'll focus later on that generalization. But out of this generalization comes this funny quantity called the curl, which has the property that it detects whether a vector field is conservative or not. So in the next example, I'll compute the curl of a vector field, and we will use it to determine if it's conservative or not.